Alright, this video I'm going to be solving 5 or so simple machine problems, and the problems are going to involve mechanical advantage. So, why not all 6? Because when I include this one in the video, it went several minutes too long, so I figured I'd just separate that off into a different video. So I'm going to look at these other 5 simple machines because they're all going to go kind of quickly. So here we go. Let's talk about the easiest one first, and that is probably, I guess that's the inclined plane or the ramp. So how do you figure out the mechanical advantage for a ramp? All you have to do is take the length of the ramp, that's this number, and divide it by the height of the ramp. So how long the ramp is divided by how high it takes you. So just to keep the numbers easy, let's say that this is 4 units long, meters, inches, whatever, doesn't matter. And let's say that it's 1 unit tall. So the mechanical advantage is 4 over 1. It is 4. So what does that mean? That means that if you were just going to take this box and you were just going to lift it up 1 unit, it would, it would be a certain level of difficulty. And if you use this ramp, it would be 4 times easier. So let's just say that this box was a 10 kilogram, or if you wanted that in newtons, it would be, what, 10 times 9.8, so that would be 98 newtons. It would feel like 10 divided by 4 kilograms. In other words, it would feel like 2.5 kilograms, or it would feel like 98 divided by 4 newtons, and what's that? That is 24.5 newtons. So that's it. So the ideal mechanical advantage for a ramp is 4. And what does this I mean ideal? That just means that we're not worrying about friction or any other energy losses. So there's 1 down and 4 to go. Let's do the seesaw or the lever next. What's going on with this one? Well, the equation is just as easy. It's just one thing divided by another thing. And in this case, it is the length of what we call the effort arm. That's where you push. That's the effort arm. It's the length of the effort arm divided by the length of the other side, the side that you're going to use to lift something. So maybe you're going to, use a fulcrum, a little pivot point here, and you're going to try and lift up a heavy box. This would be the end where you would push down on it, and this would be the end where the heavy box would be. So the effort arm where you push, let's just keep the numbers the same as this other example. Let's say that this end is 4 units long, and let's say this end is 1 unit long. So in this case also, the mechanical advantage is going to be 4. So whatever you lift, once again, it's going to feel 4 times lighter. So if you had a 10 kilogram box sitting here, it would feel like 2.5 kilograms. Or if you were doing newtons instead, it would feel like a quarter of 98 or 24.5 newtons. Okay, so that's 2 down. And really, 4 out of these 5 I'm talking about today are pretty much, in my mind, they're kind of the same. So let's do wheel and axle next. For the wheel and axle, it's a lot like the lever and the incline. Look at the equation. It's just big R divided by little r. So where do those come from? Right here, this is the size of the wheel. That's the radius of the wheel from the center to the outside edge. And then here, the little r is from the center to the outside edge of the axle. That's the skinny part. So where would you see something like this? Maybe in a well house, or just a well, I should say. So there's like a bar here, and there's a rope that goes around here that goes down to a bucket underground or something that's you're going to bring out some water. And so what's going on here is when you take your hands and you move this crank around in a circle, this bar here is going to go around in a smaller circle, and that's going to make the work feel several times easier. So if I recycle these same numbers one more time, if we say that this big radius, the wheel, is 4 and this little axle is 1, well, we're going to have a mechanical advantage of 4 again. So if we go to my crappy drawing of a well here, where you're trying to draw water out of the well, if this is 4 times longer than this radius, it's going to be 4 times easier to lift that bucket up than if you just had to lift the bucket up yourself. Okay, so next, the wedge. another easy one. So the wedge, it's just the length of the wedge divided by the thickness at the end that you're going to hit. So like, you know, if you've got a piece of wood that you want to split, you're going to use a wedge to do it, and you're going to hit it with a hammer or something. Yeah, I might as well go all out with the bad drawing. There we go. So if you want to split this piece of wood, how many times easier does the wedge make it? Well, it depends on how long the wedge is and how fat this end is. So just sticking with my same easy numbers, if we say that this is 4 units long and it's 1 unit thick, then the mechanical advantage is 4. So it would be 4 times easier splitting this piece of wood with this wedge than without. So just to step backwards for a second to one of my other videos, what if instead this wedge were longer? What if it were, you know, 6 units long but only 1 unit thick? Well, then that would be like this. And the mechanical advantage for this one would be 6. So it'd be 6 times easier to split the wood. But what would the cost be? The cost would be that with this one, you're going to hammer the wedge in that distance. But with this one, you're going to hammer the wedge in a greater distance. So if you're going to make the work feel 6 times easier, you're going to have to move a greater distance. So that's kind of the price you have to pay for making mechanical advantage higher. Okay, I think this is my favorite one. My favorite simple machine is the pulley. And here's why. Because you can do all kinds of wacky stuff with the pulley. It just can make you so much stronger. I mean, I guess it's true for any of these machines. Like with the lever, there was this guy a couple thousand years ago that said if you had a lever long enough, you could move the earth. And yeah, that's right, but, you know, where would you stand? Okay, there's my bad joke. Anyway, with a pulley, let's say that you've got this one right here. And if you're trying to let's say you're standing right here and you're going to pull this rope down, then this box doesn't seem any lighter at all. The mechanical advantage is just 1. So why would you want to do this? Well, the reason why is maybe you have a bad back and you can't bend over and pick up this box. So this pulley right here, it allows you to lift the box up when you pull down. So this is just an example of using a simple machine to change the direction of the force. Okay, so there's a mechanical advantage there is just 1. But now let's look at this one. This one's more interesting because now if you're standing here and you're pulling this rope up, what's going on here? You're holding up half the load, and the ceiling where the pulley is hooked to on the other side is also holding up half the load. So the mechanical advantage here is 2. It actually feels half as heavy, or you could say twice as light. So if you take that reasoning, you've got an extra rope here holding the weight up other than you. What if you started adding more and more pulleys? Like over in this example, we've got 4 pulleys here. So let's say that we were standing down here at the end of this rope, and we were pulling down. Well, the ceiling here and these other pulleys, how many ropes are holding up the weight other than mine? 1, 2, 3, 4. So in this case, the mechanical advantage is 4. So this box is going to feel 4 times lighter because there's 4 ropes holding it up other than mine. So in this case, it would be the same as our problems were up here. It would feel 4 times lighter. So what would the cost be? Well, you'd have to pull a lot more rope to lift the box up, but it would feel a lot lighter. So there you go. There's 5 of the 6 simple machines, how you would solve some problems, and I will post the other video for this one very soon.